So this is another question related to DC motor. As you can see in the question, figure 9.1 shows a simple DC current or direct current electric motor. The coil rotate about the axis. When there is a current in the coil is connected to the rest of the circuit by the carbon brushes. So a supply is there, carbon brushes are there, split rings are there, a rectangular coil mounted on the axle, and there is a permanent magnet. On the figure, draw a pair of arrows to show which way the coil rotate and explain the direction you have chosen. First thing, to identify the direction of a rotation, the first thing to identify the direction of the rotation, we have to identify the direction of current. And what is the direction of the current? Remember, the current always, the conventional current is always from positive to negative. So when we'll pass the current will pass through these carbon brushes and then through this first split ring, and then it passes from positive to negative. This is the direction. The red arrows are representing the direction of the current. Now we want to find the direction of the force, because without identifying the direction of the force, we cannot identify the rotation. So how to identify a direction of the force? So for that we have to use Fleming's left-hand rule. So according to Fleming's left-hand rule, my index finger should point in the direction of a magnetic field, which is south on the right-hand side. My second finger represents the direction. So if I label the sides, example, if I'm saying on my left-hand side, it is A and B, and on the right-hand side, it is C and D. So my index finger is pointing towards south. My second finger represents direction of the current from A to B. So what is the direction of the force? The direction of the force for A and B, that is downward. And what is the direction of force for C to D? It is obvious that it will be opposite if we work out one. So from magnetic field is from north to south. The direction of the current is from C to D, which is outward. And my thumb is pointing up as a result. So as a result, the thumb is pointing up, so it will experience the force upward. So on figure, draw pair of arrows. So when we draw pair of arrows, so we have to draw two arrows. One is pointing downward, another one is pointing upward. And explain the direction you have chosen. So why we choose this direction, why we say A and B is the experiencing a force downward and C and D is experiencing a force upward. So using the Fleming's left-hand rule, the index finger, the first finger, represent the direction of magnetic field. The second finger represent the direction of the current, and thumb represent the direction of force. So using the Fleming's left-hand rule, our index finger pointed in the direction of magnetic field, our second finger represent the direction of current, and thumb represented the force. So using Fleming's left-hand rule, we work out the direction. So for A and B, the direction of the thumb is pointing down, where C and D, the direction of the thumb is pointing upward. The second part, on figure 9.1, draw an arrow to show the direction of electron flow. So what will be the direction of electron flow? Electron flow is always opposite to direction of conventional current, and electron flow is always from negative to positive. Only the arrows should be there, which you draw for the first part. Then we have to show electron flow. So electron flow is in opposite direction. It is always from negative to positive. If they ask to draw an arrow to show the direction of current or conventional current, it should be from positive to negative. And explain why electron flow in the direction you have chosen in A2. So why we say electrons are flowing in this manner? Because electrons are negative. So they're attracted towards the positive terminal of a battery. The electrons are negative and they're attracted towards the positive terminal of battery. That's why whenever we draw an arrow to show the direction of electron flow, so that is always from negative to positive. Is it clear, this question? So another question is there. The question is, state any difference of each of the following change that make to the rotation of the coil in the figure 9.1. So this is figure 9.1. Remember, left hand side is positive, right hand side is negative. Now what we did, left hand side is positive, right hand side is negative. Now what we did, we made left hand side negative and right hand side positive, like we changed the terminals. So what will be the effect of changing the terminal? So if we change the direction of the current, what will happen? The direction of the rotation will be opposite. Like first it was example rotating anti-clockwise example. Then if we change the direction of the current, the conventional current, so now it will rotate clockwise. So if we change the changing the polarity of a power supply or the direction of the current, so it will rotate the coil in opposite direction, or direction of the rotation of a coil will change. Now changing the coil to new coil as 9.3. So now, like example, originally we were having only one turn, but now we increase the number of turns. So what is the effect of increasing a number of turns? It will increase the force experienced by the wire in a magnetic field. As a result, it will increase the speed of rotation. So it will rotate because it experiences a greater force. So it will rotate faster. And using a stronger magnet, when we use a stronger magnet, again, what is the effect of using a stronger magnet? A stronger magnet means it will experience a greater force. As a result, when it experiences a greater force, so it will rotate faster. So increasing the strength of a magnetic field or increasing the number of turns of a wire or increasing the area of the wire in a magnetic field, all increase, or current in the wire, all increases the speed of rotation. But if we change the terminal, that will change the direction of rotation.
Mr.
Yes.
I don't get why increasing the number of coils make it rotate faster. I know
Okay.
it makes it stronger, but faster why?
Yeah, what is the reason for that? Example, each side is, if I say each side is experiencing a force of 5 Newton, there's a current passing through. If there's a current passing through, example, this side A and B, and this was side C and D. A and B is experiencing an upward force. C and D is experiencing a downward force. Example, A and B is experiencing a 5 Newton upward and C and D is experiencing a 5 Newton downward. And the coil will rotate. Now what happened? If we increase the number of turns of a coil, each side is experiencing 5 Newton. Like example, this is 5 Newton. The other part is also 5 Newton. So what is the total upward force now? 5 Newton and 5 Newton. So total upward force is equals to 10 Newton. Same thing happened that there is a downward force on each coil. And because the current is same, so downward force on each coil is same, like 5 Newton down and 5 Newton down. So what is the resulting downward force here? 10 Newton. So you can clearly see there is a difference in the forces now. When there was only one turn, upward force was 5 and the downward force is also 5. But when we have two turns, the upward force is 10 and the downward force is 10. So when there is a greater resultant force or greater force on the object will accelerate or change its motion faster. That is why this will move at a high speed and this will rotate at a slow speed. Is it clear?
Yes, clear. Thank you.
So same thing, another question related to a DC motor. Figure 9.1 shows a simple DC motor. The direction of the current is shown to you. State the purpose of a split ring commutator. It's of 3 marks. So as I mentioned, it keeps the coil rotating in same direction by changing the direction of a current every half cycle or 180-degree rotation. So you have to include all these 3 points. Whenever a question is there, what is the purpose of split ring commutator? Then they mention the voltage of a power supply is increased. State the effect. If we increase the voltage, there will be more current. For example, if I say first there was a 2 ampere current, when there's a 2 ampere current, the force was there, say 5 Newton up and 5 Newton down. But now we increase the current, we made it like 4 ampere. So if more current, stronger magnetic field of a wire, and the force on each side will also increase. So the speed of the rotation will increase as well. So it will rotate faster. What will be the direction of the force? If I say identify the direction of force, example, we have side A, B, and this one is C and D. So I will use my left hand whenever I'm finding a force on a wire. My index finger is pointing towards south. My second finger represents direction of the current, which is according to the figure, it appeared like from A to B. So what is the direction of the force? It is like outward or upward, I can say. And for C to D, it will be index finger point towards the south. Second represent direction of the current, which is from C to D. And my thumb is pointing down. So as a result, it will experience a downward force. So one side it experiences upward, other side downward, and it will start to rotate. The next part is state and explain any motion of the coil. So you have to explain which direction this coil will move or rotate. So to identify the direction of rotation of a coil, you have to identify the direction of conventional current. So conventional current is always from positive to negative. The big line is always representing a positive terminal. It passes through the carbon brush, then to a split ring. And we have like 3 turns, so it means we want to increase the speed of rotation. Now to identify the direction of the force, because without identifying the direction of the force, we cannot identify the rotation. So example, if I say this is side A, B, this one is C and D. So what will be the direction of the force on side A, B? So to find the direction of force on side AB, my index finger should point towards the south. So that is pointing on the right hand side. Normally, as you can see, most of the question, the south is on the right hand side. So index finger is pointing towards south. Second finger represents direction of the current. For current A and B, it is pointing downward, into the paper. So my thumb is pointing downward. So as a result, what will be the direction of the force? So the direction of the force is downward for this side, and it is upward for the other side. So when I look at this wire, how I will find it is rotating? One side it is downward, other side upward, so it will rotate in this manner. So what we call this rotation, we call that as clockwise. And how to get the 3 marks? So 1 mark you will mention when the current is passing through a coil, it experiences a force and it rotate clockwise. So 1 mark is for mentioning coil rotate, 1 mark is for mentioning clockwise. And what about the third mark? That when a current is passing through a wire, the wire produces, or a current produces, a magnetic field which cuts the magnetic field of a permanent magnet and experience the force. and the direction of the current reverses every half. Like that is the purpose of a split ring. Every half cycle, the direction of the current changes. This is the second part of the question. The coil in figure 9.1, as you can see, this coil consists of 3 turns. So it is having 3 turns here. The magnetic field strength is M, the current is 2 ampere, and the coil experiences a turning effect or the force which we call T. So if we are using 3 turns, the current is 2 ampere, the magnetic field strength is M, and the turning effect is T. Now what we did, we keep the turn same, we kept magnetic field strength also same, but we changed the current. By what factor we have changed the current? It was 2 ampere, now it has changed to 8. It means it is changed by 4, sorry, not 3. So it has increased by 4. So if it has increased by 4, so what will happen to the turning effect? If the turning effect was T, now it will become 4 times the T. That's why the speed of a rotation will also increase. The second part, we keep the current same, we keep the magnetic field strength same, but we increases the number of turns. Like first it was 3, now we make it 6. So we double the number of turns. As a result, when we double the number of turns, what will happen? The rotation of the coil will also be double. And the last part, we kept number of turns same as the first one. We kept the current same, but we reduce the strength of a magnetic field. First it was M, now it becomes M by 2. So if the strength of a magnetic field is decreased by 2, what will happen to the turning effect? The turning effect will also decrease by 2. So it will be T by 2. So we have to choose your answer from the boxes. So we select 4T, we select 2T, and we select T by 2. Another similar question is there. Figure 9.1 shows figure 9.1 shows a coil ABCD with 2 turns. The coil is in a magnetic field. Explain why there is a current. When there is a current in the coil experiences a turning effect. Turning effect means moment. So what is the reason why there is a turning effect? When the wire carrying a current placed in a magnetic field. So what happened to a wire? The wire experiences a force, and this force, there is a resulting force, and this resulting force causes a turning effect. The next one, the value of the current is 3 ampere. Place 1 tick in each column of the table to indicate how the turning effect changes with change described. So in the question, we have 2 turns. The number of the turns are 2 according to the figure. And the current which is passing here, that is 3 ampere. So we have to check if the number of turns on the coil increased to 6. So number of the turns of a coil, originally in the beginning it was 2. Then it becomes 6 or changed to 6. So it is increased by what factor? It is increased by 3. So if it is increased by 3, what will happen to the turning effect? The turning effect should also increase by 3. Current become 9 ampere. So originally the current was 3 ampere, it changes to 9 ampere. So by what factor we increase the current also increases by factor 3. So if current is increased by factor 3, what will happen to the turning effect? The turning effect will also increase by 3. And then the strength of a magnetic field has decreased by factor 2. So if we reduce the strength of a magnetic field become half. So what happened to turning effect? So turning effect will also decrease by factor 2. So if we double the current, the strength of a the turning effect will be double. If we change the current by factor 3, the strength of the turning effect will also change by factor 3. So the three rules which we use, these were the questions, the three rules which we use in a magnetism. It is important that you understand when we have to use these rules. The right hand grip rule, the first one is the right hand grip rule. The right hand grip rule, it is used to find the direction of a magnetic field for a straight or a circular wire such as solenoid. So if we know the direction of the current for a straight wire or a circular wire, we can use a right hand grip rule to find the direction of magnetic field. The second rule is a Fleming's right hand rule. Fleming's right hand rule is used to find the direction of the induced current or a current produced due to change in a magnetic field. Like by moving the wire in a magnetic field, there will be a change in the magnetic field, and how we can identify the direction of the current produced due to change in magnetic field. So we'll use Fleming's right hand rule. So Fleming's right hand rule we'll use in a AC generator. And Fleming's left hand rule, if we know the direction of the current and a wire is placed in a magnetic field, so which rule we will use? We will use Fleming's left hand rule. And in a Fleming's left hand rule, our index finger pointing in the south, second finger represent the direction of the current, and thumb will represent the force. So where we use this Fleming's left hand rule, so we use Fleming's left hand rule in a DC motor. So in AC generator, it is a right hand, where in a DC motor, it is a left hand.